Okay, thanks, Jacobo, for the introduction, and so to thank the organizers for putting together this exciting program and for giving me the opportunity to present some of our recent results. And the work that I'm presenting today has been done in collaboration with Tibor Rakowski and Kurt from Kaiserlink, and the talk is mostly about these two works here. One from last year, where we introduced a new method for simulating transport at high temperatures, and a more recent work, a theory work, where it was mostly driven really by Tibor and Kurt, who came up with a theoretical explanation for why what we are doing is actually working. Good. So let me start off by motivating this project, or motivating a little bit why we were interested in this. And I think this will be a very easy pitch given the audience. So the kind of problem we are interested in is to extract universal hydrodynamic features starting from microscopic Hamiltonians. To be a bit more specific, the type of problem we are looking at is that we prepare some initial state, which could be just a very simple state, like maybe just a simple product state, and we might want to evolve it with some specific Hamiltonian h, and then the short time dynamics will be highly non-universal and contain all sorts of complicated things. When we assume that the system at long times thermalizes, then the equilibrium state will then be described by only a few conserved quantities, such as the energy or the particle number of the state. So the way, and then there's this intermediate regime where the system relaxes to the equilibrium state in a universal way. And this is exactly the regime that we are interested in. And in many cases that we know of, where we, for example, have a conserved quantity, so for example, the particle number is conserved, then we know that these systems have a diffusive relaxation. So if, for example, as shown here in the lower right, if we just create a wave package here, we just create a charge in homogeneity, then we expect that the charge will diffuse to an eventually homogeneous state, and this will go with the diffusion constant d. While this kind of generic behavior is then expected to be universal, so we would find that it decays as the square root of t, but the diffusion constant d will depend on microscopic parameters in the Hamiltonian. And the specific question that I want to address, given we have a microscopic Hamiltonian, how can we numerically extract the value of the diffusion constant? Or alternatively, also, given a microscopic Hamiltonian, how can we reach long enough times to actually show that this diffusive behavior is actually really stable and robust? So the most direct way of simulating this on a computer is to perform an exact diagonalization, or in other words, to just represent the full many-body Hilbert space and then perform the time evolution starting from some initial state. And just to provide some numbers, if you want to run it on this kind of a reasonable amount of computational resources, then we are bound to the order of 30 or so spins if we max out these simulations. That, however, is in many cases still too small to actually see the universal behavior, because in order to get to this universal regime, we need to reach certain length scales, which are often already exceeding the order of 30 spins. So here we have strong limitations in terms of the system size that we can reach. There is a nice workaround, and this is using matrix product states. So if we start from a simple initial state, for example, a product state, then of course we are not bound in system size at all for practical purposes. So we can look at really large system sizes. However, the representation in terms of matrix product states is getting increasingly inefficient if the entanglement in the state grows, which is then happening whenever we are performing this time evolution, meaning that we are now trading this exponential growth in terms of system size to an exponential growth of the complexity in terms of time. So there's now a big regime where we don't really know what to do if we just have only access to these kind of two methods. And then there is a way, some sort of at least hope that we can do better. And the hope is basically illustrated in this sketch. Because so we start now, and what we have in mind now is this representation in terms of matrix product states. So if we now start from a simple product states, we just at time 0 have a state that's extremely simple to represent for our system. And let us say that we have now a large system, little entanglement. So now we can just write down a low-dimensional matrix product states to describe the system at short times. That's good. So this is the regime that we like to be in. If we are looking at very large times, and we are assuming that the system equilibrates to a state, then we would find that at least all local observables can be determined just in terms of very few conserved quantities. So here we just only need maybe the energy or the particle number to describe the state. And there's in between a regime where things get very difficult. And the question is basically, how can we, what is an efficient way to remove this unnecessary or this very non-local information from the state, such that we can go, or that we can maybe stay inside a window where we can efficiently simulate the system on a computer, right? So basically, how can we develop an algorithm that efficiently forgets unnecessary information? And this question has been addressed by various authors, and there are various different approaches now on the market to actually try to make the algorithms forget in an efficient way. And in fact, Jens in his next talk is going to discuss this issue as well. So, and this is exactly what we want to address. And before discussing the work that we did with Tibor and Kurt, let me just first show another attempt that unfortunately didn't work out so well, but it helps us maybe to understand a little bit the ideas behind it. So what we are really good at is to perform simulations with matrix product states of small bond dimensions, right? Because then we can now consider systems that are large, and we know how to manipulate and work with them efficiently, right? So what we're just going to do is we take the amplitudes in the many-body wave function, where just by counting, you see that there are exponentially many. This is like a rank or order L tensor. So this is something that we really find hard to store on a computer, and we just express it in terms of the product of these matrices, and these matrices are assumed to have a finite one-dimension chi, and by this we just reduce the number of parameters from something that grows exponentially with system size to something that at a fixed chi only grows linearly in system size, right? So we just have strongly reduced the number of parameters describing the state. And one idea that we put forward a few years ago was the following. So instead of simulating the exact dynamics of the Hamiltonian, what we could do is we could use the time-dependent variational principle that has been introduced for matrix product states a while ago, and perform the time evolution, and don't really care about the limitations that we have. Let me just illustrate this a bit better. So we start now, and this is now shown in this view graph. So the idea is now we start from a simple state which can be represented in terms of an exact MPS. So this is this dot here. And now we just start evolving the state. And as we build up entanglement in the beginning, this state can be exactly represented in terms of an MPS. But now the entanglement grows, and we're just kind of reaching at some point the boundary of the manifold of states that can be represented in terms of the matrix product states with a given bond dimension. in a conventional approach, this is the point where we would stop the time evolution, because the moment that we reach this boundary, the simulation is biased, so we just build up an error. But the assumption to just keep going is now based on the fact that, well, if we just using this time-dependent variation principle, global conservation laws such as energy and particles are still conserved. So the idea is that, well, if we just use this time-dependent variation principle where energy and particles are conserved, a hope could be that the universal properties or the kind of hydrodynamic properties of these classical Lagrangian actually reflect the transport properties of this quantum problem, right? So this is just a hope to have. And then in that paper, we looked at a specific model, namely at the Ising model with a transverse and longitudinal field, a model that at first glance appears to be a rather generic universal model. And it turns out it works really well, right? So here we just look at the mean squared displacement. So something that we expect to grow linearly as function of time in a diffusive system. And from the slope, we can extract the diffusion constant. And we see that independent of the bond dimension, we get the same answer. So this suggests that this is a really great method, because we just forget about a lot of the information that we would need otherwise, and we just do get the universal behavior with the right diffusion constant. Well, and if something seems to be too good to be true, often it's not. and this is also the case here, where we just now use the same method on a different model. If, for example, we take an XXZ model with long-range interaction, which is a non-integrable model, where we just expect to find again that the system thermalizes after long times. If we just play the same game, well, what we see is now that depending on the bond dimension, we see that asymptotically we just converge to a straight line from which we can extract the diffusion constant. However, the moment that we leave the comfort zone of the MPS simulation, we actually get a diffusion constant that's much smaller, right? So we see in this case that the method fails to reproduce the correct results. So and in fact, this behavior on the right-hand side is the generic behavior, and all the other models except the Ising model for these specific parameters fail using this method. So which means we had to go back to the drawing board and just think about different ways to truncate the information. And this is what motivated this work, which we call the dissipation-assisted operator evolution method. And the basic ideas of this method are summarized on this slide. So what we are doing is, first, we are no longer considering the Schrödinger picture that we did before. So we're not time-evolving states, but now we are evolving operators. And at the level of the Heisenberg evolution of operators, what we do is we just introduce an artificial dissipation, which reduces the operator entanglement, and thus it makes it easier to represent in terms of matrix product states. And this allows us then to capture the dynamics to long times. And the way that we do the truncation is demonstrated here. I just briefly summarize the idea, and then I just on the following slide are going to discuss it in some more detail. So the picture that we see here, and we're going to see it again, is it basically has an L, and L is now the contribution of complicated operators. So we start from a simple operator, which could be, for example, just a simple sigma x operator. And as we evolve this operator in terms of the time evolution, we would find that the operators grow. So we just get operators that are more complicated. It's a product of many Pauli matrices. And eventually we just measure maybe another simple operator. And in the meantime, some longer operator, more complicated operators contribute. And the idea is that we just discard the information corresponding to complicated operators as we do the time evolution. So this is a key idea. And then what we can actually show is that the errors induced by this truncation are actually exponentially suppressed in this quantity L star. this was this bird's eye view. Let me just now go back and make this a bit more concrete, what I just said. So generically, we are now interested in calculating some dynamical correlation functions, right? So how some operator Q naught at time 0 is correlated with another operator measured at x and time t. And we just think now doing this at infinite temperatures. So, and this we can now express in terms of time-evolved operators in the Heisenberg picture. So let me now think about the following. So now we have this space of operators, and every operator, in particular our time-evolved operator Q naught of t, can be expanded in terms of Pauli strings, right? So now we're assuming a spin 1/2 system. So we can now just write down the whatever operator we get at a certain time, we can now expand in terms of these Pauli strings. So the Pauli strings are now, for example, the product of identities with one sigma x operator, or we can have like y operator, identities and x operator. So we have now a superposition of all of those operators. So these form a basis for all those operators. Now, if we just, now we can on the one hand do this kind of exact time evolution and just get the exact correlation functions. But then the price that we pay is that performing the time evolution is again exponentially hard when representing the operators in terms of so-called matrix product operators, or if you just represent these operators that are transformed into matrix product states. So now what we're going to do is we're going to occasionally apply a dissipator. And the dissipator is now doing the following. So we just take now our operator and we apply this super operator d, l star, and gamma. And this is not doing anything if the operator string is short. And let me just illustrate how we define the length of an operator string, or the complexity of an operator string. If there's just this single operator, like a single non-trivial operator, then ls is equals to 1. If there are two operators which are not necessarily adjacent, right? So we have now just an operator string with two non-trivial operators, then ls is equals to 2, and if now you get the point, right? So now if there are 3, so now it's y, identity z, identity x. So for this one, ls would be equals to 3. So if the operator only contains at most contains L star operators, then this dissipator is not doing anything. If, however, the operator contains more complicated terms, so if, for example, ls is equals to 2, then this ls equals to 3 term would get this exponential damping factor with some rate gamma. Good, right? So the cutoff length corresponds to the number of non-trivial Paulis in the corresponding Pauli string. And if we just simulate Hamiltonian dynamics, then we want that the cutoff length is longer than the support of the conserved quantities. For example, we have energy conservation of a Hamiltonian, like 2-spin Hamiltonian, then we need to choose ls equals to 2. Good. And now the way that we just performing the time evolution is that we perform the exact time evolution with respect to the Hamiltonian, and then we just apply the damping after a certain time. And then we just see that operators that have excursions into the space of very long operators, they will be damped. And the key assumption is that this backflow from long to short operators is weak. Let me comment on this a bit in more detail later on. So now we can now represent the dissipative evolution of these operators in terms of a matrix product evolution, or using tensor networks. So we just first represent our initial operator, which is, for example, just a simple sigma x operator acting on one side in terms of a matrix product operator. And now we can use standard methods such as a time evolving block decimation method to perform the time evolution, and operator entanglement will build up. And then at a certain time, we apply the dissipator. And the dissipator can be represented as a very simple low-dimensional matrix product operator as well. And then this is now the change that we made to the standard evolution operator. And now we can just do a test on the Ising chain. So we just now perform a test on the transverse field, longitudinal field Ising model with some generic parameters. And we see that if we now plot the operator entanglement as function of time, we see that indeed in the beginning it grows, but then depending on the damping rate, we see that then the entanglement it decays and it becomes easier to simulate. So now we can just apply this idea to this model to then extract the diffusion constant, for example, by calculating the mean square displacement. And then this is now shown here on the right-hand side. So the dotted lines we obtain from the DAOE method, where we just extrapolate the gamma value to 0, and then we just compare to exact diagonalization data. And then here we see nicely at how the exact diagonalization data is kind of asymptotically converging to exactly what the DAOE method gives. And with the DAOE method, we can reach system sizes that are large. So the system sizes are no longer a real issue. So let me now show how the data looks like. So here is now the data for the transverse field Ising model. And importantly, here we now take parameters for which the time-dependent variational principle that I showed earlier failed, right? And what we see here on the left-hand side is we see now the diffusion constant as function of time for different values of gamma. And we see that if we have gamma that's large, these are the bright values, then so these are these gray values, then we see that there's still an effect of this gamma, and then we see that asymptotically it converges to a fixed value. And if I now extract now the values that we get from the diffusion constant as function of gamma, we see that we can now extrapolate them to gamma equals to 0. Let me explain a bit the idea behind it. So now we just perform these DAOE simulations with different L stars. And for looking at the energy diffusion, we have to choose this L star to be larger or equals to 2, so that the Hamiltonian still, or that the evolution conserves energy. And then we can now, for each L star, reduce this gamma. And we know that if gamma is equals to 0, we would follow the exact time evolution of the Hamiltonian. However, then it would be impossible to simulate because of this operator growth, of the entanglement growth. If we have very large gamma, it's very easy to simulate using matrix product states, but then we see that we get stronger corrections from the backflow. And the strategy then is that we just reduce this value of gamma and then can extrapolate the gamma equals to 0 value. And this would be then the diffusion constant for the specific Hamiltonian that we are interested in. So, and here we just demonstrated for the energy diffusion in the Ising model. And here we just look at the spin diffusion in the XX ladder. And here we just compare to some large scale typicality results obtained by Steinigeweg and others. And we see that asymptotically just converging actually to the same result that they obtained.
5 minutes.
Okay, I think I'm going to say one time, thanks. Good. So we see that it nicely converges to the diffusion constant that was obtained previously from typicality results. Good. And let me now just in the end just briefly comment on these theory of backflow corrections. And this is sort of giving some theoretical argument for why this method actually works. So here there's some sort of operator Feynman diagrams that Kurt and Tibor came up with to express the physics at play. So let us say that we want to look at a correlation between some operator O0 and an operator OX. Then we have some order 1 time scale. Time is going here in the x direction. So we have an order 1 time scale for x decaying into some sort of hydrodynamic quantity, which is then moving through space-time. And then at some point, this would grow to a larger operator. And then we have now L star. So here we have now a picture where we just perform this single hard truncation. So basically we just apply here not a soft projector, but we apply here a projector projecting out all those operators that are longer than L star. Then we can calculate the probability for this operator actually reducing itself again to the simple hydrodynamic operator, which would then contribute to the correlation function. And using analytic arguments, both for random unitaries and for deterministic models, one can then argue that this backflow is expected to be exponentially small in L star. And to back this up with additional numerical simulations, we can actually see here for the XX ladder that the maximum deviation or the maximum contribution to the correlation function from the backflow indeed decays exponentially as function of L star as shown here. But this insight helps us on the one hand to understand or to basically argue why this method works, and the other hand, that helps us to understand why we get this kind of linear extrapolation here as function of gamma. Good. So let me now conclude. So we addressed the question about how can we extract kind of diffusion constants or universal hydrodynamic properties starting from microscopic Hamiltonians. And the method that we propose is performing Heisenberg time evolution using matrix product state methods. And the new addition is that we just introduce an artificial dissipation that dissipates long operators, like operators that contain many non-trivial Pauli operators. And then we just have a theoretical explanation which argues that the truncation, like the backflow, is exponentially suppressed in terms of L star. So let me thank you for your attention, and I would like to thank Tibor and Kurt for this collaboration.